Welcome to a lesson with Dr. Powell. Let's talk about quaternions. They are an analog to the complex numbers. Now, the complex numbers are great for describing arithmetic using things that are two-dimensional, multiplying and adding numbers that represent points on a plane, and they could also represent vectors from the origin to a point. Now, what does I do when it acts on a vector? Well, it outputs something that looks like this, which happens to be, if we take a dot product, 0. What does that mean? Well, if a dot product is 0, that means the two things are perpendicular to each other. Now, we're going to use the word orthogonal to each other instead of perpendicular to each other. They mean the same thing, but orthogonal is used when we go up to higher dimensions, more than 2. We want an analog for the complex numbers, but in 3 dimensions. Is it possible? Can we do it? What did we do here? Well, I is an operator on a vector, and it switches coordinates and makes one of them negative in a nice way to make something that's orthogonal. So something that's perpendicular to what we started with. It is rotation by 90 degrees in a counterclockwise direction. We want operators over here that behave the same way. And we'd like to be able to describe numbers just as we did over here with something plus something else, but maybe with 3 things instead of just 2. Is it possible? Try as we might, it actually isn't. It doesn't really work very well. In order to make this process work, we have to go up to 4 dimensions. Okay, we're going to have a vector, which will be represented by a tuple of 4 things. The last 3 coordinates will represent our x, y, and z, and the first one will represent a real coordinate. And these we'll call imaginary. So we just have one direction being real. So what does I do? I will be an operator now. And the way it'll work is it'll switch the first 2, switch the second 2, and then make one of them negative like this. Look what it does to the unit vector in the real direction. So length 1 vector in the real direction. It interchanges it to a unit vector in the next coordinate. We'll just call that coordinate I. It'll represent x. Notice that if we do I twice to something, I squared, well, let's just interchange these again and interchange those again and make things negative. The first entries, we get a -1 here, which means that I squared is equal to -1, just like we had for complex, which is one reason why we might call this direction right here imaginary. Okay, and great, this type of switching and negating gets us a dot product of 0 every time. So it really does work. It really gives us something that's orthogonal, like a orthogonal type of rotation, but it's in 4 dimensions, a 4-dimensional rotation. Okay. Let's get the other coordinate. We define another operator, j, interchanges things in this way, negates, and we end up getting the next coordinate. And again, j squared is equal to -1. Do the same thing again for k. And we'll just let k be we just let k be do one operator after another in the following way. Okay, let's keep going. These I, j, and k's work very nicely together. I squared, j squared, k squared is always equal to -1, and we can do I times j, get k in that particular way as we define what k is. But notice that j and k actually give us -j in the definitions that we gave for the operators. So we get that that one direction is negative of the other direction when we multiply. We can summarize that in this little circle. I times j is k, but k times j is -I. I times k is j, k times I is -j. Well, let's see this in action and remember what I, J, and K do. They're operators that make things orthogonal. If we add some of these together, it again becomes an operator that makes things orthogonal or perpendicular. So anything that doesn't have a real part, like I plus J plus K, we'll call imaginary. And when we multiply by it, it'll produce something that's completely orthogonal to what we started with. Let's look at an example. Let's take this imaginary quaternion, has no real part, and this quaternion that has a real part. Notice how we write these things. It's a lot like complex numbers, right? But we have more imaginary parts, not just one. We have an I and a J and a K part. So when we multiply these two things together, we can distribute. But maybe a good way of doing that is in a table. This is first, so I'll write it out here. Order is important, remember, because if you interchanged order, even on the table, things were different. So we have this guy first, I, negative J, K. And then this over here, negative 1, 2I, negative 3J, and K. And respectively, we go through the definition of how the table was given. I and I is negative 1, J times I, going around J times I will actually be negative K. So a negative K, but then times a negative 1, that's why that one's positive. So we go through that, and we get all of these, and we add like terms. Adding like terms, we end up with this quaternion as the result. And you can check. This quaternion dotted with the quaternion we started with right here is 0. They're orthogonal, meaning this actually rotated this guy to a perpendicular direction, just like when you multiply by I, the complex numbers, it makes your vector be orthogonal to the other one. So we have this nice type of arithmetic that happens, and we have a way of describing the coordinates in 3 dimensions as an imaginary part of something that has 4 parts to it in an addition. Thanks for watching.